Welcome to Honeyniga High School. I'm Brian Brown, and today we'll be looking at Chapter 5, which deals with the electrons in the atom. Now, in Chapter 4, we looked at the general structure of the atom, and we placed the protons and neutrons in the nucleus, but we really didn't say where the electrons were other than outside of the nucleus. So where we were at was basically where we were at in the early 1900s, where we had discovered the fundamental structure of the atom, but really there was a lot left to find out about the total structure of the atom because we really didn't know much about the electrons. So in Rutherford's work, he had come up with this uh, idea that the positive charge of the atom and virtually all of its mass was located in this very small nucleus surrounded somewhere by fast-moving electrons. So really, in order to continue to develop our nuclear model, we needed to have a better understanding about where electrons were outside the atom. And because of this, scientists in the early 20th century really found Rutherford's nuclear model to be incomplete. And they felt that our true understanding of the atom, we really need to have a better understanding of what was going on with the electrons. Well, as it turned out, in order to understand electrons better, we first had to have a better understanding of light. So scientists at the time found out that, surprisingly to them, light is actually two different things at once. It's an energy form, and energy forms have wave-like properties, which is what we traditionally felt was true about all energy forms. And a particle, basically, or a matter, I should say, is a particle and has particle-like properties. But what scientists found out was not only does light behave like it's a wave, but in some situations, it actually behaves like it's a bundle or particle of light, which we call a photon. So light actually behaves as both a wave and a particle at the same time. And this was a huge change in science. And that really opened up our eyes to maybe think about and understand the electron in better ways. So to understand the electron, we're first going to get a better understanding of light. Now, by classical physics, light, which is visible light, so when we say light, what we're really talking about is light that the eye can see, is a form of energy that exhibits wave-like properties known as electromagnetic radiation. Now, electromagnetic radiation, and light is only one type of electromagnetic radiation, is actually a series of different types of electromagnetic waves that can travel through a vacuum. So they don't need a medium to travel through. They can travel through a vacuum like outer space. And they move at a constant speed, 3.00 times 10 to the 8th meters per second, which is really flying. I mean, that's almost 3 billion meters every single second. So you turn on the flashlight, and that light 1 second later is, almost 3 billion meters away from you. Now, the reason we call it electromagnetic radiation is it really deals with the fact that this type of energy wave has electrical and magnetic components to it. And it deals with oscillations in the electrical and magnetic fields as it moves through space. Now, the fundamental types of electromagnetic radiation that you should have a good understanding of in first year chemistry would be radio waves and microwaves, infrared waves, visible light, ultraviolet, X-ray, and gamma rays. And I want you to have a working knowledge of these different types of things because they all play a role in many applications in everyday life. Now, if you take a look at the full electromagnetic spectrum, down here on the far side, and you'll notice this is the low frequency side, and one of the things I'm going to mention often tied to that is it's also low in energy. So as we go across the electromagnetic spectrum in this direction, we're talking about things that are first lowest in frequency and in energy. And you'll notice wavelength, which is another property of waves, is the exact opposite. And that's something we're going to be getting into more in future discussions with electromagnetic radiation. So we start out with, on the far left, we have radio waves, which would be our lowest in frequency and energy of the types of electromagnetic radiation that we're going to look at. Now, what is radio waves? Well, if you think about what happens at a radio station, you first have a person that makes sound, and that sound radiates out. But sound can't travel through a vacuum, and it's not moving at the speed of light, so it's not electromagnetic radiation. But a microphone then takes that information and codes it electronically and digitally, and that then gets transmitted to the outside world by the tower at the radio station. And that's where we have electromagnetic radio waves. So what's coming out of that tower, which we can't see because our eyes can't detect it, is radio waves. And radio waves are our lowest frequency and energy type of electromagnetic radiation. So once it leaves the tower, it's actually moving at the speed of light to your radio. And what your radio does is translates that signal that it detects in the air back into a digital signal and then translates that through the speaker into sound once again. So they're basically undoing what they did in the first place. But in between those 2 points, from the tower to your radio, that's where we have radio waves. And radio waves take up a relatively large chunk of our electromagnetic spectrum down here. And that's closely regulated by the federal government and the FCC, because one radio station in an area can transmit, but if another radio station is transmitting at the exact same frequency, you're actually going to hear both sounds overlaid on top of each other. So what you can broadcast at and how strong your signal is something that's closely regulated by the government. So there's lots of uses for transmitting information in the world around us using radio waves. Now, a little bit above radio waves would be microwaves. Now, when you think of microwaves and microwave ovens, that's really only one particular frequency of uh, electromagnetic radiation in the microwave spectrum. And since that magic frequency that makes the bonds in water molecules vibrate, which makes the water molecule vibrate, which means if you're making it vibrate faster, you're heating it up, and that's what cooks your food. Well, that's one frequency that does that in all of the different parts of the spectrum that are microwaves. And radar are also in this part of the spectrum as well. So if you've ever been pulled over to get a speeding ticket, they were bouncing radar waves off you to detect what your speed is. So microwave and radar waves are in this part of the spectrum. And remember, a microwave oven only operates at one particular frequency, which is that magic frequency to make a water molecule vibrate and heat up. And that's why your microwave oven doesn't work unless you have something inside it that has some moisture in it. It has to have water in it. So if you put a dry paper plate in your microwave oven, it's not going to do a thing. But get it wet and then put it in there and you'll feel that it heats up. Now, I had already also mentioned that, radar waves are in this part of the spectrum. Well, so is your cell phone. What we're looking at here is a cell phone microwave relay tower. Now, microwave radiation is a line of sight type radiation. So we have to basically send it straight line from you to the tower, and then from that tower to the next tower, and that tower to the next tower, and then from that tower to whatever cell phone is nearest. So basically, when you're calling somebody at a specific number, you're finding out, okay, which cell phone tower are they nearest, and then you're setting up a link of communications from your phone to those cell phone towers to the other phone. And the type of radiation it's sending is microwave radiation. So your phone uses microwave radiation. It's just not at the same frequency that your microwave oven operates at. Otherwise, that potentially be bad for you because you've got lots of water in you. Now, above microwave and radio waves would be infrared. Now, infrared is heat. So heat is in the infrared part of the spectrum. So when you get close to something that's very hot, you may not see anything coming out, but if you put your hand over by it, you will feel heat radiating out. Well, if we could see into the infrared spectrum, we could see that electromagnetic radiation that we're detecting with our hands. And that's what this is a picture of. This is an IR photograph of a dog. And you can see the different parts that are in transmitting infrared radiation in the form of heat much more strongly than in other parts. So if we could see into the infrared spectrum, we could actually see heat in the world around us. Now, above infrared, we finally get to visible light. Now, before I move off infrared and microwaves, one last thing. If you have a clicker for your TV or any type of remote for things around the house, if when you use it and you put your hand over the top of it, it stops working, it's probably an infrared type of device. So it's actually sending out infrared radiation to communicate with whatever is nearby. But if you cover your hand over the end and it still keeps working, then what you probably have is a microwave system. So in your home, certain types of products will communicate in the microwave, and those can actually penetrate through things better than something like infrared would. Your portable phones. So if you still have a landline at home and you've got a phone that you can take off the base and walk around, it communicates to the base through a very specific frequency of microwave radiation. So above microwave and infrared, you would then have visible light. Now, I've got this clicker up here shown, and you see this light coming out of it. Well, remember, infrared and microwaves are too low in energy and frequency for us to detect. So what you're actually seeing when you press the button is a dummy light. And that dummy light has a very important purpose. We wouldn't know if the clicker has dead batteries if we didn't have some kind of evidence, like a light that lit up when you pressed it that no longer lights up. Then you would know you need to change batteries. So if it was microwave or infrared types of radiation that you're using to transmit to your TV and other devices, Usually it has a dummy light on it that lets us know when we're using it if the battery is any good. So once we get above that, then we get to visible light. And this is a little bit exaggerated here, but visible light is really a fairly narrow band of the electromagnetic spectrum. But if you break that band apart, you get all of the colors of the rainbow, the ROYGBIV. And once again, the ROYGBIV, red, orange, yellow, green, blue, indigo, violet, that's a way to remember light in a very specific order, which would be increasing frequency and increasing energy, and therefore decreasing wavelength. So the ROYGBIV, I know orange light is higher in energy than red light is, and so on. Now, visible light basically is a really important part of this overall spectrum, because right here at that visible, we go from lower energy types of light that aren't really interacting all that much in a negative way with atoms or cells inside our body. But anything above visible light is high enough in energy to be considered ionizing energy. When that electromagnetic radiation hits an atom, it can cause the atom to be ionized, which means it's knocking electrons around. So that type of fundamental change in an atom can be very dangerous inside the human body. So ionizing radiation, anything above visible light, is actually more dangerous to us. So when we get to ultraviolet radiation, which we've all heard of, you've heard UV light is dangerous and you shouldn't go out and get tanned too much. Well, that's because the tanning process is your body's mechanism to basically absorb and protect you from ultraviolet radiation. And until you've built a tan, when you get hit with UV light, that UV light could be damaging your cells. Typically, it kills the cell, but there is a very small chance that it might lead to a mutation in the cell rather than killing the cell. And if that mutation is viable and survives and no longer functions like it used to and starts attacking the surrounding body, then you can develop a melanoma or skin cancer. So once we get into the ultraviolet part of the spectrum, now we're dealing with types of radiation that are potentially harmful to us. So you wear clothes and you use sunscreen to help protect yourself from that more dangerous type of radiation. But it also has some beneficial effects. In the case of in our lab, well, every time you use your goggles, well, maybe somebody's gotten bacteria or viruses on them that could be transmitted. Well, when I put it in the goggle cabinet, shut the door, and crank that knob around on the side, it sprays the inside of the cabinet with ultraviolet radiation, which will very quickly then kill any viruses or bacteria that may have been stuck to the goggle. So when you get it out and use it again, it will be clean. Now, once we get above ultraviolet, now we get into X-ray radiation. Once again, this is higher energy ionizing radiation. So when you get an X-ray, you're exposing yourself to dangerous radiation, which is why they have you cover yourself with a lead vest and the person leaves the room and so forth. So why are they doing it if it's potentially dangerous? Well, it's a cost-benefit thing. If you have a broken bone or if you have something seriously internally wrong and an X-ray can show you it, that's much more important to know than the slight statistical increase in contracting certain types of cancer that exposing yourself to an X-ray would entail. So really, it's a cost-benefit situation, which is why if you're a female and you're at the dentist and they ask you that embarrassing question about may you be pregnant, well, the unborn fetus is a fast-dividing cell which is very susceptible to this type of high-energy radiation, and it could do severe, severe damage to the fetus. So it's very important if you might be pregnant. Well, it's not worthwhile at this point to find out if I have a cavity or not using an X-ray. So you use other techniques that aren't as potentially harmful to the unborn fetus. But it is something that is really, really beneficial at potentially saving your life in other types of situations. So they have to be careful about when and how they give you X-rays. And then above X-ray radiation, the highest in energy and frequency would be gamma rays. Now, gamma rays, while they're very high in energy, we really don't worry about them damaging us because they're so penetrating. They basically move right through our body without us absorbing that energy, unlike X-ray and ultraviolet radiation. So gamma rays are basically things that stars spray out across the universe, and that gamma radiation goes right through planets and so forth. So it's a very penetrating type of high energy radiation. And what you're actually looking at here is a gamma ray look at the universe on edge, our galaxy. So Earth is probably somewhere over around in there. Now, those are different types of electromagnetic radiation. And what we looked at was lowest in energy and frequency up to highest in energy and frequency, and wavelength would be exact opposite. Now, the ROYGBIV is a way to help us remember that Visible light comes in red, orange, yellow, and so forth, increasing frequency and energy. Well, how to remember the electromagnetic spectrum? Well, one way would be to use an acronym kind of like ROYGBIV. And this one is Red Martians invented very useful X-ray guns. So red would be radio, and then microwave, and then infrared, and then visible, ultraviolet, X-ray, and then finally gamma ray. So this is an acronym kind of like ROYGBIV that can help you remember the electromagnetic spectrum and remember them in order of increasing frequency and energy, because you may see a question on the test related to this. Hint, you will see a question related to this. And ROY-GBIV is another type of acronym, but it's just one that most of you have heard to help us remember the visible spectrum in increasing frequency and wavelength. And as you approach the violet, the frequency and therefore the energy of the wave is increasing, and its wavelength is actually decreasing. So what really are waves? I've been using terms like frequency and wavelength, but what are those properties of waves? Well, all waves share certain properties like wavelength, amplitude, and frequency. And we concentrate on the first and the third here. Amplitude, which deals with the intensity of the light, isn't something we typically look at all that much. So wave properties. First off, wavelength. The symbol for wavelength is the Greek letter lambda, which kind of looks like this weird looking giraffe. And wavelength is literally what it says, the length of the wave. Now, waves basically follow this oscillating motion through space. So that's a wave as it propagates or moves through space. So what is a wavelength? Well, we look at the distance between corresponding points on side-by-side waves. So if this is like the middle of our wave function, and that's a middle, that would be one wavelength. That's one oscillation, up and down rotation, or up and down propagation of our wave. Now, it's kind of hard to find the middle, so a lot of times what we do for wavelength is we look at top to top, which would be the crest of the wave. That would also equal our wavelength, or bottom to bottom, the trough of the wave. So that's what wavelength is. The length in meters of basically one wave cycle. And for many of our waves, these are very, very small numbers. Like in the visible part of the spectrum, the wavelengths are actually very, very small things. So instead of meters, we sometimes use other things, like nanometers is a common one that you're going to see. A nanometer is, like a millimeter or a kilometer. It's just a way to change the prefix, and it means 1 billionth. So 1 nanometer is 1 billionth, 1 times 10 to the negative ninth of a meter. Now, amplitude, I mentioned the one that we're going to use least, would really be dealing with the intensity. It's the height from the origin, so this imaginary middle spot right here, to the crest. That would be what we consider the amplitude, and it really involves the intensity of the light. Now, frequency, on the other hand, besides wavelength, we also look at frequency a lot, is the Greek symbol or the Greek letter nu, which looks kind of like this weird looking V thing. So typically when you see nu in most of our fonts, it's going to be kind of an odd looking V. So that would be nu, which stands for the frequency. Frequency is like frequent, how many waves pass a given point per second. So a non-electromagnetic type of wave that may make it easy for you to think of frequency would be an ocean wave. Obviously, ocean waves have to have water, so they don't travel at the speed of light and they don't travel through a vacuum. But if you're standing at the end of the dock and you count how many wave cycles passed crest to crest in a given amount of time, what you've actually done was measure the frequency of those ocean waves, because it would be how many waves pass a given point in a given amount of time. Now, in the case of electromagnetic radiation, what we use is how many pass per second. Now, when you look at a per second, that's going to look like this as a unit, 1 over s. Well, sometimes people are confused and they don't like fractions all that much. So what we've actually done is instead of calling it a inverse second, what we actually call it is a hertz. But 1 over s, which is the same as s to the negative 1, which is the same as hertz, those are all representing the same thing. It's a frequency, and it means waves per second. So if your frequency is 430 hertz, that's for 430 waves passing by in a second. So 562 hertz would be 562 1 over s, which would be 562 s negative 1. All are the same thing. They would be representing a certain frequency. So usually we don't see the 1 over s. Usually we see hertz, because like I said, we try and dummy it down to make it less confusing. Now, if you've ever listened to FM radio stations, they actually broadcast in the megahertz frequency range. Well, that would be 1,000,000 hertz. So something like WZOK is 97.5 megahertz. So that literally means 97.5 million hertz. So we, like with nano, for wavelength, we sometimes use abbreviations like mega with frequencies to make them normal numbers. And that's something that we'll end up talking about next day of notes when we get into doing some calculations with wavelength and frequency. But I believe that is our end of our first set of notes.